to E, the exit velocity, minus the inlet velocity, plus your pressure term, which is P exit minus P. And this is the final equation that we use. So if I know for an air-breathing engine, I know my mass flow rate going through the engine, which is a very critical parameter that you need to know. You know your fuel-air ratio that you're putting in. Then based on that, you get the exit velocity. You know your free stream. This is known because this is your aircraft velocity that you're flying at. This is your computing based on the condition that you're doing through a reaction. This is something that you're controlling. This is a very critical parameter. And this is based on your area of your engine that you're already designed. This is the inlet pressure, so you don't control that. The exit pressure and the exit velocity are the two things that you control: the fuel-air ratio and fuel-air ratio. So from there, you have your thrust. Now this is equation 5.6 of the book. So let's do the same exact problem for a dual bypass stream engine. So I'll keep this up here. Let me do. So propulsion system. With two exhaust streams. So what we just did primarily is turbojet engine, which is primarily built for aircraft. But right now we're doing a dual exhaust system. It's mostly a commercial aircraft. So this is really a turbojet. The other one is a turbojet. And we're going to go over them in more detail, but just right now we're outlining our equations. So if I have my nacelle right there, this is the shell of the engine. I have a big massive fan at the inlet right here. The thrust is actually coming from that fan. And we'll do the efficiency and all these things that go on. You're going to actually vary bypass ratios, and you're going to find really interesting things. I have my compressor right here. I have a shaft going to my turbine right here. I have a combustor right there. Okay, so compressor, burner, turbine, fan. Okay, so we want to isolate this by two streams. So it's the same thing that we just did with the turbojet. The difference is now I have to bookkeep my mass and momentum for all the different streams that I have. But I have two main streams. I have a hot pour flow, should have wrote it inside, and a cold flow core. No combustion. So, what's happening is, oh, I forgot to do the shaft. So what's happening is you're spooling up your compressor, you're burning inside the burner, you're generating expansion through your turbine is spinning, and you're getting high velocity here, but you're also driving the shaft that does work. That work actually drives this fan, and this is primarily your desk fan. So happens here is this fan sees the free stream velocity and it accelerates that velocity, but that velocity just moves the engine and comes out in the end. This velocity actually is much higher because you're actually keeping it up. So, in reality, if you draw this in terms of vector field, this is what it's going to look like. And this is what this is going to look like. And my free stream velocity now that we already know this what happens when it goes around, so we don't really have to worry about it anymore, is much smaller right here. Coming in.
Sweet.
Now let's define some masses because I think it's going to be confusing. So we have a total, bless you, we have a total exit flow, meaning that this is m dot exit hot, this section there, okay? And this and this are both m dot exit cold. Okay? So I could say m dot exit is equal to m dot exit hot plus m dot exit cold. And in terms of momentum in general, I could just say, well, u exit, m dot exit is equal to my u exit hot, because the velocity of the hot is different, multiplied by m dot exit hot plus u exit cold multiplied by m dot exit cold. Okay, so now m dot exit cold is equal to m dot inlet cold, right? So what is m dot inlet cold? It's right here. It'll be a section right there. This section right there. So those two are your m dot cold, which is based on your flight Mach number, as I said, coming into the fan. Mass is conserved, whether you're accelerated or not, still mass is conserved. So what comes out as cold is going to equal to what comes in as cold. Think of it as just a straight dot. That's your fan flow. It's just, it looks complicated by having that core inside, but this is why we do all this review, because you get a lot of these bookkeeping of mass and momentum and it gets messy. So m dot exit hot is equal to m dot inlet for the hot section plus the fuel that I'm routing fuel in there, so m dot fuel. So let me draw m dot hot. So right here, this right here is your m dot area hot, or m dot inlet hot. Hot, sorry, not exit. Okay. So this is this. I'm bringing in fuel. So what I'm saying is this is equal to this plus the fuel, which is the same thing that we just did. So the derivation that we just did earlier is this. Now we're adding the outside duct core to it. So when you write the conservation of momentum for this equation, this is your conservation of mass, well, tau is equal to, we'll keep all of them, I have m dot exit hot multiplied by the velocity of the exit that is hot, section, from the hot section, plus the exit of cold, m dot exit cold mass, multiplied by the velocity of exit cold, minus, that's my exit, minus my inlet, which is the summation of both masses but multiplied by velocity, so m dot inlet hot plus m dot ambient cold multiplied by the velocity plus the change in pressure. And what do we have? We have the exit pressure from the hot core minus the ambient pressure. This at section area hot plus the rate of change in pressure for the cold core, the cold section. So the P exit cold minus the ambient is equal to may multiplied by the area of the cold section. So let me highlight the areas. So this area right there with the top one is area exit cold, and this area right here for this section is area exit from the hot section. So let's rearrange the terms and substitute some of our masses that we have over here. Inside, what do we get? We get tau is equal to m dot AC multiplied by the U exit of the cold section minus the U inlet of this plus m dot inlet for the hot section, H multiplied by my 1 plus fuel to air ratio of my exit velocity from the hot section minus my velocity of the free stream plus the difference in pressure. So PEH minus PA. Area exit H plus your PEC minus PA. And this is the final equation that we're going to use for bypass. Now that doesn't mean anything, because what if I have dual fans and I could change multiple ducts, but you know the process of how to drive this. And this is what's critical about advanced technologies, because that's what you do. You don't. It's not a cookie cutter like recipe. I could add multiple ducts in there. All I need to do is just bookkeep the same process of how I'm driving my equation. Does that make sense? Okay, so this equation is equation 5.7 in the book. Now, we're going to tailor this a little bit more later on when we actually go over turbofans by the bypass ratio. Which is beta. And the bypass ratio says, well, I have two masses here. If I compare my equation that I had before, right here for turbojets, we only have the inlet mass that's going through my engine. My area, the air that I'm slugging through the engine specifically. This is primarily okay for military engines, but for commercial engines, we're after higher efficiency. So to do this, we have to rely on a bypass ratio. And as I mentioned earlier, most of your thrust for your commercial engine comes actually from that fan, your desk fan. That's what it is. The engine is just primarily spooling the percentages, and you're going to play around with these later on and see how much thrust you're producing from the core versus the bypass. And depending on our bypass ratio, the reason, well, we'll talk talk about it when we get to turbofan. But the bypass ratio controls the mass ratio,
Fan does all the work and the engines do it.
which is cold relative to hot. Now, what does that mean? It means how much mass am I really? So what this says is the ratio of the duct mass versus the actual engine core mass is what drives quite a bit of how much fuel I'm dumping in versus how much I'm really producing as thrust by purely driving that fan. So the more you have this, the higher your bypass ratio, and the more efficient your system actually becomes. Because then you're just using work to directly drive the fan versus actual heating up the flow to produce thrust. And we'll see this later on. But that's our, let's say, main parameter for turbofan. We'll talk about it once we get to turbofans. Now, one thing to keep in mind, the exhaust top core pressure is equal to P ambient, and the exhaust cold core pressure is also equal to P ambient. So that's something to keep in mind because we can substitute this and get our specific thrust. So let's define specific thrust. So specific thrust is equal to my thrust over my total area that I'm actually putting through my engine. So let's do it for the turbojet right here. This is the equation that we have. Well, what's my specific thrust? Well, it's equal to 1 plus my fuel air ratio multiplied by U exit minus my U flight velocity, the free stream, plus area exit multiplied by P exit. This is divided by M dot A. And this is for the turbojet. Now, for the turbofan, so this is single stream, i.e. turbojet. Now for two stream, this is equal to tau divided by M dot A as well. But M dot A is the summation of the multiple masses that I have. Now, multiple masses, you realize if I divide by my total mass, in certain scenarios, I can substitute it in terms of beta. And that's what I can get as a equation there. That's equal to beta over beta plus 1 here. So based on the definition of the end up core exit inlet, multiplied by UC minus U plus 1 over beta plus 1 for this case, and multiplied by my 1 plus fuel air ratio multiplied by my U exit minus my U of the free stream plus my pressure ratios, which is going to equal to the exhaust pressure minus the ambient pressure divided by and A multiplied by my exit of the hot port plus my delta P as well, PC minus PA divided by m dot A multiplied by the area of the core. And that's a specific thrust for a two-stream membrane. And all it is the same thrust equation that we just derived right here, normalized by how much air am I really inputting into my engine, and what is my bypass ratio, which drives how much, think of it this way, how much am I doing for my fan versus how much am I doing work through my core for a thrust perspective. So based on this, let's define some of our key parameters for our engine. So these are the basic principles. So let's define our TSFC, which is a parameter in propulsion engines. Sure.
Just turn it on.
It depends on the scenario. So, yes, that's absolutely correct. But I'm saying that it could potentially be equal depending on what you're doing as a design. So you're right now doing the project, right? The project, you have a shock at the end of the exit. So the exit of the core engine. So I'm just listing the generic equation. But when you're solving a problem, if the ambient pressure is equal to my exit engine pressure, what happens there? It just goes up, right?
Yeah.
So it's a good question. So Hunter is asking is, most likely you're going to try to do your engine that the exit pressure is equal to your ambient pressure, but that's not always the case. So for military engines, you're always going to have oblique shocks at the exit. Or you're going to have a normal shock. The problem that you're doing, you have a normal shock at the exit. So that's not your exit pressure. The exit pressure is different than what's outside. So you have to, I'm listing the generic equation, but if they're equal, then these terms will cancel out. But I need to list the equation that you're eventually going to use. So with all the terms. But if these are equal, that drops out. And that's a good point. When that drops out, what happens? All your thrust is just coming through your velocity difference. How much you really accelerated that flow inside that engine. And that's what propulsion is all about. Remember the boat. All we did was take a piece of rock and throw it off. And that's, where is it? Right here. First day. Right there. So, just take a piece of rock and throw it away. That's all propulsion. Did anyone try this?
So it's just a momentum thrust. Action on it. Pressure. Exit equals pressure.
Both
Let's
runs
say
that again.
5. But just make sure whatever mass you put in there is
I don't think that goes. So it's only momentum that's driving it.
Anyway, so that's why, yes, these terms could potentially cancel out, but not always, so keep it in mind.
I like the feeling.
And the reason I said they're equal back pressure for turbofans, primarily because, well, you
Totally
don't really
understand.
have to deal with shock
They
waves for
totally understand.
turbofans, because they're not military engines. So,
She.
for now,
Didn't you read it?
right, until we
Oh, yeah.
need, you know,
That's good.
supersonic speeds for commercial flights. But
It
it
means
still
you can
depends
call them
on the
into
scenario
this
they have to use. Anyway, so let's define thrust specific
changed
fuel
my mind.
consumption.
Thrust.
This is one of the acronyms that once you're in the industry, you forget what it really stands for. TSFC, that's all you know is TSFC, but it really stands for thrust specific fuel consumption. That's a very key factor there. Because whether you're doing military engines or commercial engines, you're most likely your customer, whether it's an Air Force or Boeing or Lockheed, and they come to say, well, I have an aircraft that weighs this much and I need to move it at this much thrust. So here's the thrust value, and I want to maintain a TSFC of this value. So you go and design the engine based on these parameters, which you go back and tailor your area ratios, your pressures, your fuel airs, your bypass ratios, and all that based on these parameters that you get as an output. So what is TSFC? TSFC is equal to how much fuel I'm dumping into the engine relative to thrust. Very, very simple, straightforward equation. Now, what do we want to do in general, whether we're military engines or commercial engines? Do we want to increase that value or decrease it? Decrease? Just how much fuel I'm putting in relative to the thrust I'm producing out of that engine. So the more fuel you put in and you're getting less thrust, that means your engine is happy, right? So you're going to minimize.
Engine shit. Alright.
So meaning that you're running a car engine with 3 miles per gallon and you're only getting 10 horsepower. That's what TSFC represents.
What the fuck?
If you're trying to, if it's going up, right? But you want to minimize it. You want a 100 miles per gallon car with 1,000 horsepower.
Yeah, right.
So that's what you want to minimize. So that's what TSFC really represents, that ratio that I just used an analogy there. So a very key equation that we're going to use throughout. Now, propulsive power. Propulsive power, really, power is work, which is equal to force times distance. Now, how does that translate in terms of my propulsion system here? And I'm just listing it so you don't have to memorize these. But it's work. Work is force times distance. So how do I translate it in terms of the work that I'm producing there? Well, my work is, it's a rate, and it's equal to force, which is my thrust, multiplied by my velocity, which is my distance. Obviously, velocity is meter per second, and that's why I converted it to rate. So my propulsive power, W dot P is equal to tau multiplied by velocity. And that's my propulsive power. How much I'm really producing in terms of power through my engine. Available power.
Some flight mechanics.
Power.
There's power required.
Okay, available power. Well, it's the rate of